We rolling? There we go. Well, thanks for joining us, everybody. This is the first one of these I hosted. I was saying before we started recording, this is a colloquia series that the NAU folks at MIRA started last semester when we joined partnerships as part of the NNCI, funded by the NSF for 5 years. And so they held an exciting set of talks as the colloquia series last semester. And so this year, this semester, ASU's got involved. So we're going to have a mix of talks from NAU faculty and ASU faculty. And so I'm pleased that our inaugural ASU faculty member is Dr. David Ferry. And a number of people present today were recruited to ASU by Dave. So it's a genealogical history family tree that we were talking about. Dave's a Regents Professor. I was looking at his, can I share my screen?
Sure, should be able to.
So here we go, here's Dave's bio. So you'll see here, he was one of the first groups of Regents Professors at ASU. And actually, you officially retired a couple of years ago, right? But you know, we can't tell any difference. Dave gets in here early at least before COVID, Dave was in here every morning early, meeting with students. I think the only difference is you don't have to go to faculty meetings or sit on committees.
I don't have to grade papers and teach class.
And you get free parking, right?
I get free parking on campus.
So that's excellent. So yeah, and very interesting bio here. I will leave you to read it, but the thing you may want to notice is that David is an admiral in the Texas Navy. That's a rank that not many people can boast of. So I will finish there and hand it over to Dave, and hopefully he can start sharing his screen.
I can share my screen now.
And we were talking, we'll encourage people, if you have a question, if something interesting pops up, please, I don't know, somehow let us know and we can ask Dave to helpfully.
Well, I would prefer you ask questions as we go along, because that way I won't have forgotten it by the end. Okay, so it's a privilege to be here, and you can see I'm going to talk on hot carrier solar cells and non-equilibrium phonons. And I'll explain most of that as I go along. And from the picture you can see, I hope everybody's got their margarita or their Mai Tai or a glass of wine and got themselves settled in to enjoy this as we go along. One of the nice things about COVID, you're not strictly with the on-campus rules about having a drink while you're going at this. All right, so I'm a Regents Professor Emeritus, as Trevor said, and I've been on this topic here. I've been collaborating with Steve Goodnick at ASU and some experimentalists at the University of Oklahoma, Ian Sellers and Vince Whiteside, no S. And so I need to thank them for a lot of this that goes along. Now, let's see if this will move. I guess I have to use this over here. Yes, this is me, if you can't see up there. And that scene behind me is a reminder of nice places. That's actually a restaurant in the first district of Vienna. It's an Italian restaurant and maybe 50 to 70 meters out the front door of St. Stephen's Dome in Vienna. So, but I have to say the guy I was with couldn't focus his camera. So it's a little out of focus. Okay, now what I would like to talk about is, at least in this talk, is the narrow world of solar cells. So I'll give a general introduction to solar cells to kind of get everybody up to ground zero. And then I'll talk about hot carrier solar cells and why they're of interest. And then I'll talk about the role of non-equilibrium phonons, which are very important, as we will see in the hot carrier solar cells. And I'll talk about what we know, and perhaps what we don't know about non-equilibrium phonons. Okay, so that's kind of the outline that I want to go along in here. Now, this is allegedly a solar cell. It's a PN junction. The most common kind uses silicon. This white line down here, can you see my cursor?
Yeah, we can see it.
Okay, great. So that white line is the depletion region that's built into the thing. And that's a very important area because that's where the voltage drop in the junction exists. And there's a high electric field there, as we'll see in a minute. So light comes in, some of it bounces off the surface, some of it gets absorbed. And that which gets absorbed creates electron hole pairs. And the electric field in this depletion region separates the electrons from the holes. So the electrons go one direction, the holes go the other direction. And for each photon, you get 2 particles of current, which flows out and into a load over here on the right-hand side. Now these white lines up here are contacts because you have to have a contact to get the current out. And that's kind of a good days, bad days, half full glass type of thing, because the contact has to be large enough to carry the current without too much resistance. But if it covers the whole surface, the light doesn't get in because the metal reflects the light back. So that's where the trade-off has to come. And so, and in addition, the silicon surface will also reflect some of the light. So you use anti-reflection coatings there, just like on your glasses, to help the light get in. Okay, that's a normal PN junction. Okay. Now this plot is just to tell you that there are a lot of approaches to solar cells. You got purple lines, blue lines, what happened there? Green lines, dashed lines. It's all very chaotic. The one certain thing you can say is if you go to any one of these places and ask them who makes the best solar cells, they will tell you they do. Okay, that's a universal thing in all fields. Of course, the best work is done at home. So there's a lot of approaches. It's best, the world is chaotic this way, and you shouldn't try to learn any one of these type things, but just be aware of it. Now, this is the so-called Shockley-Queisser limit. That's this black line that comes up over the top. We'll explain the bumps and wiggles a little bit later. But these are mostly single crystal, single junction cells. Crystalline silicon, amorphous silicon, gallium arsenide. And the Shockley-Queisser limit was worked out many years ago by Bill Shockley and Hans Queisser, basically on a thermodynamic argument, which shouldn't be really all that important for solar cells, but it seems to have survived. So if you get 75% of the limit, you're down in this green area. If you can get 50%, and you're in the pink area. And if you live down here, you're probably not going to sell many cells. Okay, so if you were going to do, a lot of the cells you get don't make this thing, but they're cheaply made with amorphous silicon. If you can afford the gallium arsenide, for example, if you're the DOD or NASA and you can afford the cost of these cells to be out in space and get the extra efficiency, you'll do that. And so that's a big support there. Okay, so this is kind of the thing that everyone in the world is trying to get past, this black curve. So if we can get over that, we will revolutionize the world of solar cells. Now, this is the spectrum. The top black curve is what the sun puts out, and what you will see if you're above the atmosphere in the space station looking at the sun. You get this nice black curve. It's a Bose-Einstein distribution at the sun's surface temperature of about 5,400 Kelvin. And it's relatively smooth. What gets to the surface of the Earth, though, that's this next black curve. That's at sea level with the sun directly overhead. You see a lot of absorption in the atmosphere, which eats up a lot of the photons that can come in. Silicon band gap is right here. This is photon energy. So photons above the red, up on this side of the red line will be absorbed in silicon. On this side of the green line will be absorbed in gallium arsenide. Now, this curve at sea level, as the sun goes down, you get this dashed curve. And you see the last bit down here is green, and that's why you have a green flash. If you can see it when you're looking at the sunset in places like Hawaii or Monterey Bay in California. It's an actual real event, although most people think it's myth. But the green flash occurs because the last bit of the spectrum you lose as the sun goes down is the green part. Okay, now, this is the problem with today's solar cells. This black down here is that Shockley-Queisser bit. And the bumps and wiggles here are due to the atmospheric absorption. So this is based upon what gets to the surface. It's commonly called AM 1.5, which is a designator for the type of solar spectrum you're using when you look at your cell. Okay, now if you raise the band gap of the material too much, you lose this part of the solar spectrum. And so you can't get any energy out of all that light that's coming down with these photons below the band gap. So that's not good. The green part is what we're trying to worry about. The green part is what's going to be our phonon losses, relaxation of band edges. I'll explain that phrase in a little bit. And this is other losses, reflection at the surface, metal blockage, things like that. Okay, so the task is to get out of the black and get up here. If I could cut off the green part and use a band gap down here, I might reach 80% efficiency. And that would totally revolutionize the solar cell world. Okay, so now PN junctions are different than solar cells. Okay, so now, can you see the right side of the screen?
Yes.
Yes.
Because I have people's picture also all over the right. I suppose I can move it to the, oh, that's what I'll do. Okay, so then I can see, all right. So the PN junction works like this. If you put a forward bias on it, right, electrons from the N-type region are injected into the P-type region where they're minority carriers, and they're going to move by minority carrier diffusion. Same time, holes are injected from the P-type region into the N-type region where they are minority carriers, and they will move by minority carrier diffusion. Okay, and you note the direction they're going, opposite the electric field. Now, for the solar cells, photons come in and they create electron hole pairs. And if these electron hole pairs are in the depletion region of the junction, then the electrons will move down the potential surface into the N-type region where the majority carriers. And the holes move up down their potential thing into the P-type region where they're majority carriers. So they're going to move by drift rather than diffusion. And if the photon gets absorbed out here in this contacting region, you create an electron hole pair, all right, but they don't separate because there's no force to separate them. So they have to diffuse to the depletion region, and that's not minority carrier diffusion, that's ambipolar diffusion. And so it's a different mechanism diffusion and has a different speed at which the particles diffuse. But if they can reach the depletion region before they recombine, they can separate. Now, silicon cells need this area out here to absorb photons, and you need the ambipolar diffusion because the absorption coefficient in silicon is weak. If you have a 3,5 cell, where the absorption coefficient is large because of the direct gap, you can make the whole solar cell just the depletion region with proper ways of design. And so you can get a lot better behavior that way. So those are some of the things that are differences. Now, okay, all right, I'm back to this. Okay, for example, here's gallium indium arsenide at room temperature. This has a band gap of about 3/4 of a volt. And you can see up in here, 10 to the 5th, silicon will never get up to 10 to the 5th. It's down in this region because of its indirect gap. But if you get to 10 to the 5th, that means the average electrons being absorbed in 1/10 of a micron. First 1/10 of a micron from the surface. So at 3/10 of a micron, 300 nanometers thick, 95% of all the photons coming in have been absorbed in the gallium indium arsenide. And so that's good. You want to try to do that and keep all these electron photons in the material where they're going to be useful and in the depletion region. So you want the depletion region to extend over those 3/10 of a micron. And you do that by doping. Okay, so that'll make a good cell. So we're back to this, relaxation of band edges. So let's talk a little bit about what this means, okay? Okay, this is a material, I think this is indium aluminum arsenide. It's got a gap just over a volt, about 1.1 volts. So if I take a 2.5 volt photon, it excites an electron out of the valence band here into the conduction band. Now at this point, it's got a lot of high kinetic energy. And so what it promptly does is it emits a lot of phonons. That's this bouncing thing. And the phonons are about 35 millivolts in energy. And so they're going to emit enough phonons to get down here to relax at the bottom of the band. That's the relaxation process by phonon emission. Now, the holes do the same thing. I've just not drawn them here. They rattle up and then they can recombine across here if we let them do that. But all of this phonon emission is loss. That's going into heat, not into the load that you have the cell on it. So that's all the losses. That's that green loss that really eats up all the energy from the photons, is this phonon emission. So the goal would be to stop this phonon emission by some way or the other, okay? That's part of the goal of the hot carriers. Now, the hot carrier solar cell was conceived in 1982 by Ross and Nozick. Brilliant idea, good people. And to establish such a cell, it was proposed that one needed to prevent the thermalizing through the emission of phonons, cut off that phonon rattle down in the bands, right? By some mechanism or the other. One way that they talk about, as we'll see in a minute, is what's called a blockade. And I'll explain that too. And extract only the hot carriers through an energy selective contact, okay? So for the last 40 years, engineers have been scratching their heads to try to manage ways to cut down phonon emissions by the carriers and various superlattices to create energy selective removal of the hot carriers. And in that 40 years, they haven't got anything, okay? It's still a field waiting to happen. 40 years ago, Ross and Nozick suggested if they could get these two things through, they might reach 80% efficiency in the solar cell. Now, 40 years later, we're still hung up on Shockley-Queisser. We're not going anywhere. So we need to do something about that. Now, about a year ago, the first step is you want to stop this cascade from rattling down here, right? You need to stop that with some type of phonon bottleneck. That's the first thing that they proposed. Now, we suggested about a year ago, rather than using a bottleneck, the electrons that are sitting up here want to transfer over here to the satellite valleys. These are metastable valleys. And the electrons will stay there for several picoseconds. And in several picoseconds, these electrons can travel a micron. So you can get them out of the device without them ever going back to the central valley of the conduction band. So we send them to a satellite valley. And that stops this cascade because they don't need to emit so many phonons. So you're going to save about half or 2/3 of that cascade by putting the electrons over here in what we call valley photovoltaics. Put them over here and get them and extract them from here so you achieve the second part of the Ross and Nozick as well. So we made some progress on this valley approach to hot carriers. It appears promising, but as yet, just like the Ross and Nozick, they don't work well. So we're trying to figure out what that is. And we hope to have some solutions. There's a new design that's in test now. Ian promises me we'll have data within a few weeks. I say to Ian, you're not driving your graduate students hard enough. Got to get the whip out and keep them working. So in the meantime, let's talk about the phonons and what a phonon bottleneck entails, okay? So let's go learn a little bit about phonons. So what are phonons? Phonons are vibrations of the atoms in the lattice. There are optical phonons and acoustic phonons, okay? Now, silicon has 2 atoms per unit cell. All the zinc blend have 2 atoms per unit cell. And so that means that there are both optical phonons and acoustic phonons in the silicon and the 3,5s and other materials too. And here's what it is. The optical phonon at the zone center, notice, is that 2 of these are in 1 unit cell and they're vibrating against each other. Okay, now the acoustic modes move together. It's a long wavelength oscillation. This is a very short wavelength oscillation, which is why it's called optical, because it has a high energy, 35 millivolts or so, and these are a few millivolts. Now, over here at the zone edge, or over here, it's a little more complicated. This is an optical branch and this is an acoustic branch, but in the zinc blend materials, you have a heavy atom and a light atom. Gallium and arsenic. Arsenic is heavier. And this branch, the heavy atom is sitting still and the light atom is vibrating around it. Okay, and here, the light atom is sitting still and the heavy atoms are vibrating around it. So they're slightly different. And so that affects how the electrons themselves in the band structure get from one side to the other, but it's an interesting aspect of how things are going. Now, if we look at the spectrum, this is the spectrum for indium phosphide. Actually, it's for any 3,5 semiconductors, but it's drawn for indium phosphide. This is the optical branch. This is also an optical branch. This is in plane motion, longitudinal. This is the two transverse because you have 3 dimensions in the crystal. So the two transverse are doubly degenerate. Okay, this is the acoustic branches. And these are the transverse acoustic. Now note this splitting up here. This splitting does not occur in silicon. Okay. But it does occur in compounds, most compound semiconductors like zinc blende. It occurs there. And that's very important because it tells you something about the material. And what it tells you is that the lattice is polarizing in the electromagnetic fields. In other words, there's charge on those 2 atoms that causes a polarization vector in each unit cell. Now, electrical engineers know about Maxwell's equations. D is the electric flux density. Epsilon is the optical dielectric constant in the material. This is the electric field intensity. This is the polarization. Now, if we say the polarization is linear in the electric field, which it isn't always, but if we say it is, then we can write this as a susceptibility times epsilon. And 1 plus that susceptibility gives you a contribution to the dielectric constant, which separates the 0 frequency static dielectric constant from the optical dielectric constant. So the 0 frequency is higher dielectric constant because it has a polarization in it. And that's related to those 2 phonons. In fact, this thing is called the Dane-Sachs-Teller relationship. And if your phonon spectra and your dielectric functions don't match with this equation, then you've got something wrong. So this is your sanity check between your phonon frequencies and your dielectric constants that you're using. Now, if you take a material, for example, like moly disulfide, a monolayer material, you'd say, well, it's a metal, moly, and a couple of chalcogenide atoms, sulfur, and they should have different charges and they should have something like this, but they don't have any polarization because at 0, at the gamma point, which is the small k where you're going to get photons into the system, these 2 dielectric constants are exactly the same. And these 2 frequencies are degenerate. And so there's no polarization in moly disulfide. And that means that the scattering process from that polarization, which is called the Froelich interaction, doesn't exist in moly disulfide. So that's an important thing. If you look at this spectrum, you see, that's a strange material because you would expect things that aren't there. So it's a kind of a sanity check. Okay, so the LO mode scatters via Coulombic interaction from the polarization. And in the gamma valley where the electrons are created by the photons in the solar cell, it's the largest scattering process there, except for the scattering from gamma to the satellite valleys, which is bigger because of the large masses and density of states in the satellite valleys. But for that phonon cascade, this LO mode is dominated by the phonon cascade in 3.5. Now, that means that it's so efficient in emitting phonons, these phonons will be driven out of equilibrium. So they'll get away from their normal equilibrium distribution and they're no longer Bose-Einstein in shape, but something much different when they're out of equilibrium. Okay. Now we can look at that. This is indium phosphide. This is excited by a laser 1.96 eV. It's a 0.6 picosecond pulse. And it's being measured 2 picoseconds after the pulse. And so this is the measured distribution. I'll tell you a little later how it's measured. This is the measured distribution for the phonons in indium phosphide under this condition. And it's much, much larger than the equilibrium population, the Bose-Einstein. It has nothing like a Bose-Einstein distribution. It's dramatically different from the black body radiation distribution you expect for Bose-Einstein. So you have to worry about things like that. Okay, so the shape of distribution, and that arises because when the electron interacts with the phonon to emit the phonon, there's a maximum value of phonon wave number and a minimum value of phonon wave number that you can interact with. And that's because of conservation of momentum and energy that's in the Fermi golden rule. And so that maximum and minimum are separated roughly by the width of this peak. And you can see 1 is 10 to the 6th per centimeter wave number. So the photons are 2 orders of magnitude bigger. So they sit at gamma. Okay, so Now we can write an equation for the time response of the phonons. Time rate of change of a phonon distribution is the generation rate from the electrons. So that's the net emission rate of the electrons emitting phonons into this mode. And we'll make this more exact a little later, but this is a relaxation of the real phonon from its equilibrium value with a lifetime. Now this phonon lifetime depends upon the manner in which the LO modes can decay into acoustic modes. And because you need to conserve energy when you're going from optical to phonon, it's a minimum of 3 phonons involved. The one you're emitting and 2 more in the acoustic modes to take it up. So 3 phonon processes come from the 3rd order elastic constants of the material. When I was young assistant professor, I wanted to study this lifetime, and I went to my physics department and found an expert on phonons. And I asked him about 3 phonon processes, and he looked at me like I'd asked him about, are there men on the moon? And that's when I realized people just don't study them, but it also means if you don't look at these 3 phonon processes, you can't describe thermal conductivity either, because that's a 3 phonon process. So often this stuff isn't taught well in schools and graduate schools, so it becomes important to find ways. So anyway, let's get on with this. So what is this 3 phonon process? Okay, well, there's several of them. Okay, this is that same spectrum for phonons I had before. Now, the oldest process known to us is the Clemens process, which is this blue curve. So 2 near 0 momentum LO phonons decay into 2 LA phonons with equal and opposite momentum. So the LA phonon has to have half the energy of the LO, okay? So the 2 of these add up to that energy, and the equal and opposite momentum give you nearly 0 momentum. That's called the Clemens process. It's the oldest. Then Brian Ridley came along and said, well, wait a minute, I could decay into a TO mode and a TA mode with the opposite momentum and still conserve energy. So that's the red curves, and that's the Ridley process, okay? And so then a Frenchman and an Italian working together, which is kind of a recipe for disaster, I think. But Valle Bogani has the green one, said I could decay into an LA and a TA mode with opposite momentums and still satisfy momentum. Well, this was not seen much. And we'll see in a minute that the red one actually just dominated the wurtzite crystals. Okay, so you have these various processes of decay. Now, people have thought about cutting off the Clemens processes by looking for materials where this LA peak here is less than half the LO peak. They want to do indium phosphide, but they haven't checked the data. It doesn't satisfy. I mean, indium phosphide still has the Clemens process. The only material I know of where you might cut off the Clemens process is indium nitride, and possibly gallium nitride too, but that doesn't mean you're going to cut off phonons. Okay, so how do we measure those distribution functions and lifetimes? We do it with Raman scattering, okay? So what's Raman scattering? Here's my photon coming in, that's the red line, creates an electron hole pair, and they can recombine either after absorbing a phonon, which gives you the anti-Stokes line, which has a higher energy, or by emitting a phonon, which gives you the Stokes line, which has a lower energy. Okay, now let me move this so I can see my equation now. Okay, all right. So the anti-Stokes is proportional to the phonon distribution. Anti-Stokes is an emission process, so it's a phonon distribution plus 1. Okay. Now, if you wonder where the plus 1 comes from, go back and study your harmonic oscillator in quantum mechanics book, and because that's how you get the phonons, is you just treat them as a bunch of harmonic oscillators. And so the emission of energy into the harmonic oscillator is proportional NQ plus 1. Taking energy out of the oscillator, out of the harmonic oscillator is NQ. Now I can look at these and I can take this ratio, IS over IAS minus 1, invert it, and I get a guess at what NQ is. So I can measure this as a function of the momentum of the photons coming in, and therefore get the distribution function and the amplitude. And Raman scattering is done this way. This is one way. Have a laser. We used 1.96 in that last example I said. We use a beam splitter. So most of the signal goes through, powerful pulse hits the sample. A small fraction is taken off, maybe amplified if it's too small. goes through a movable reflector so you can slow it down and delay it relative to the first pulse, bring it back and run it through the sample and do Raman scattering with this probe pulse. Now you can actually use different lasers if you get them phase locked together, because you have to keep them time synced in order to do the experiments. So Raman scattering, and Frank Sen in our physics department did all the Raman scattering work in the years when we were doing this type of work. So I collaborated with him for maybe 20 years on this stuff. Okay, now let's see, where am I next here? Okay, so this again, this is hitting that, this is now indium arsenide, but we're using that 1.96 EV laser, 0.6 of a picosecond pulse width, and we're measuring out here at 8 or 10 picoseconds afterwards. And why is it so slow that way? That's because the electrons with that high a laser energy, they go to the satellite valleys where they stay for several picoseconds, then they come back and start driving the phonons out of equilibrium. So in order to match the experiment's the blue dots. And there's actually a blue dot under this red one, but it's exactly under it, so it's masked. So there's a peak here at about 8 picoseconds, okay? And then there are 3 other curves, and they're for these conditions, and they're done with ensemble Monte Carlo techniques. It's all reported here in this paper 25 years ago. The phonon lifetime, we need that, and we need the coupling constant between the gamma valley and the L valley where the electrons are being stored. And so we can play with that since it's never been measured. We have an idea what it is. So we have 1.8 picoseconds, 10 to the 8th, 1.8 picoseconds, 10 to the 9th, 4 picoseconds and 10 to the 9th. And we get a Goldilocks effect, right? If it's too small here, it comes up here, peaks a little early, and it falls off too rapidly below the experimental points. On the other hand, if we use 4 picoseconds and 10 to the 9th, we get the orange curve, which peaks too late and lays above the experiments. But if we use 1.8 and 10 to the 9th, just right? Just like Goldilocks said, it's just the right temperature and it lays right over the experimental points. So that gives us some values for these things, okay? And that's a value, actually, today we use a slightly smaller value, as I'll show you in the next slide. But we can get these values for a lot of materials. And it turns out they have some common characteristics. Get this over here again. All right, so here's a lot of materials: gallium phosphide, gallium arsenide, indium phosphide, indium arsenide, gallium antimonide, cad telluride, zinc blende. All these blue are zinc blende materials. The gallium nitride, indium nitride, aluminum nitride, cad sulfide, those are all wurtzite materials. And I'll explain that a little more later. And you can see these kind of line up on this black line, okay? Now, you might say, is that just a black line you've drawn through these? No. It's not. The black line actually follows D, the lattice parameter. This actually isn't the lattice constant between the 2 atoms. This is the edge of the cubic cell. Okay, but that's just a fractional constant, a geometrical constant different from the lattice constant. So that's just a shift. Okay, but this comes down as a 10th power. Now you say, my God, that's a big power. So what are we doing? Well, it turns out, remember this, we have the decay of the optical phonons goes with this 3-phonon process. And if you look carefully in your solid state physics books, sometimes you have to go back to Cattell, to the early editions of Cattell to find this. But there's the statement that the 3rd order elastic constants depend upon the bulk modulus to the -5th power. Okay, and the bulk modulus is directly proportional to the lattice parameter. So since the scattering rate is the square of the matrix element, that makes the bulk modulus to the -10th power, okay? And so you get this curve, and that's fit, okay, to that. And this is the one with gallium nitride. Now the zinc blends look pretty good. The wurtzites, though, they're all over the place. Gallium nitride and indium nitride are doing what they're supposed to do. Aluminum nitride and cad sulfide, anybody's guess. I mean, tend not to like aluminum compounds anyway, because if you leave the aluminum surface bare, it oxidizes. And so you get all kinds of crud on the surface. So that's a problem with that. But there's a scaling parameter in this for the lifetimes of the phonons. And so you can generally check and see if it fits with what you expect it to be in your measurements. Okay. Now, back to this curve. This is the equation I showed you before. Now, this expands to the emission of phonons by the electrons minus the absorption of phonons by the electrons. Now, the emission is proportional NQ plus 1. Emissions proportional NQ plus 1, absorption N sub Q. Okay. Now, here's how you create a blockade. N sub Q is usually small. Here it's really big, 0.05. But on the scale of 1, that's still a small number. But if I could get NQ up above 1, so these two terms start to cancel each other, then I create a blockade when the electrons can no longer emit phonons. And some of that has been seen in quantum wells with laser excitation back in the, I think it's in the mid to late 80s. And so it's possible to start slowing down the electron emission, but a true bottleneck, as you see, is kind of a catch-22. I get a very large part of Q, and that cuts off further emission by the electrons. But a very large part of Q means I'm losing a lot of energy into heat. And so it's good and it's bad. So it's not necessarily the way to go at everything. Okay, now let's come back to can we determine which process is involved? Okay, we have the Clemens, the red is the Ridley, and the green is the Vallée-Bogani. Okay, so the answer is yes, we can. Let's come back to that decay constant. Let me go back to this term right here, and let's write it more effectively. So here's the 1 over tau. This is the emission process, emission by the LO into an absorption by the 2 other phonons. And the reverse process is absorption of the LO and emission by the 2 other phonons. And you work all this out, you discover it's kind of like the LO mode population 1 plus the other 2 populations. Now these can have different energies in the different processes. In the Clemens, they have the same energy, and so they have the same temperature dependence. In the Ridley, they have different energies and they're going to have different temperature dependencies. And that's the key. So with the data that we want to show you is taken on gallium nitride and its wurtzite. Okay, this is the wurtzite unit cell. Now the thing about that is you have A1 and E1 LO modes. One of these is in the basal plane, got to get it, in the basal plane of the wurtzite, and the other is perpendicular to it. Okay, but the electrons interact with both of them. Okay, so they both get driven out of equilibrium. Okay, now you see here that from LO that there's a big gap down to the acoustic, so you could actually cut off the Clemens mode, right? And so we would expect to see Ridley dominate, and in fact, that's what happens. The blue points are data points versus lattice temperature. So you can see this. And the green curve is the Ridley decay, and the red curve is Clemens, which doesn't fit the data. Now, we didn't expect Clemens to be very important, but Ridley certainly seems to still be very, very active. And you can see in gallium nitride, the phonon lifetime varies from 5 picoseconds at a few Kelvin to a little less than 3 picoseconds at room temperature. Now it's worse than that because the nitrides have this very unholy property, which we've discovered in hemps and heavily dosed stuff, that this lifetime is dependent upon the population of the electrons. The lifetime gets shorter as the electron density gets higher. And we don't understand that. At least I don't understand that. So we had done gallium nitride early and got this 3 picoseconds. And then the Lithuanians said, well, you know, in hemps, we measure much less than that. So Frank got a series of doped materials and we did the full doping density from 10 to the 16s up into the 18s. And yeah, Lithuanians were right at the high density and we were right at the low density. So we found that out the hard way. Okay. All right, so where are we going next? Okay, here. All right. So can we say anything about the secondary phonon distributions? That is the LA and TA modes, or the TO modes, and so on. The answer is yeah, you can say a little bit about it. This system here is what's called ultrafast electron diffraction. Okay. And sometimes you need a free electron laser to make all this work, but that gives you the ultrafast X-ray diffraction as well. But this is, let me explain this to you. This is a laser oscillator, and it's a mode locked laser. So it pulses at 75 megahertz. You get a laser pulse out 75 million times per second. And you detect it, and so you send the 75 megahertz pulse signal into a phase lock loop. Okay. Now, part of the oscillator comes to an amplifier, which is another mode locked laser, giving us gobs of power coming out, because we're going to split this into 3 beams. The first beam splitter is here, so part of this pulse comes off and it comes around this loop, and there's some delays and phase shifts, and comes down here and blasts the photocathode. Okay, so it's a pulse of laser light blasts the photocathode and gives us a pulse of electrons, a big blast of electrons. Okay, now part of this then comes over here, up here, another beam splitter, and this can be moved. So that's a delay, which delays this pulse. And this is more delay, which delays the bit it comes around this way, which is over here, pulse from the top, pulse from the bottom. And these 2 interfering pulses makes a grating. And this mixes with the grating of the crystal, okay? And then comes the blast of pulse of electrons through here in sync with all these laser pulses, and it scatters, it diffracts off these gratings, right? And so you can see what happens here. This is in graphene, right? Because it's scattering of electrons off surfaces of monolayer graphene is the best thing to do, or molybdenum or something like that. So here's the hexagonal unit cell of graphene repeated over places. This is 100 direction. This is off in the 1100 to another one, but these are all repeats of the gamma points. This would be the Brillouin zone, second zone, third zone, and so on. And so the bright red is where you're seeing strain in the crystal, okay? And the strain is observed by these phonons right down here, which are blown up here. So the ZO prime here is what's called LO prime up here. LA comes down, TA, and TO prime. What ZO means is that's vibration normal to the graphene plane, okay? So you have these phonons, and this really bright thing says you're exciting phonons in the gamma point. That's this point right here. So that's these phonons are being driven out of equilibrium. And those are going to be the secondary phonons in decay of big LO modes from up here. They're going to go down to here in some of these. So you can actually measure these and see how far out of equilibrium they are. So that's graphene. Here is molyditelluride, and same type of stuff, this ultra-fast electron diffraction. The molyditelluride also has a hexagonal unit cell. The electrons sit at K and K prime, these edges, the corners of the hexagon. This is the gamma point, okay? M is the center of this space, and this lambda between gamma and K is sometimes called T or U in papers which I've written. So I believe T is what the old time band structure people called it, and then later they used U, and now we see it's called lambda. Okay. So anyway, and then here is the rise time of the strain in the crystal, which gives you a lifetime at the lambda point, at the M point, at the K point. That's for 400 nanometer laser. Here's an 800 nanometer laser, and this is what's seen in diffraction, and here's those lifetimes over here. So you can see they're a lot shorter lifetimes than up here. So you can get around and measure those. This is all real new stuff. You see, this is 2019 work. That's, you know, that's just barely pre-COVID, right? So it's relatively new work. So, okay, it's almost 4 o'clock. I guess it's what, almost a quarter till. So hot carrier solar cells have been predicted. For them to succeed is control of the phonon populations. But non-equilibrium phonons are ubiquitous in a great many devices besides hot carrier solar cells. They're in HEMPs, MOSFETs. Marco's down there in the audience, and he had a graduate student trying to work on a Boltzmann equation for phonons in gallium nitride HEMPs, as I remember right. So he's been interested in this for a while. So, and we can learn a lot by studying the phonons. It can drive you to distraction or to seek drink, but we can still learn a lot by studying it. And there are many approaches to this study, but we still have a lot to learn in this area, and new experimental techniques are coming up. So with that, I'll be very happy to answer any questions people may have held off on till now. Trevor?
Well, thank you very much, Dave. We have to give you a virtual round of applause. So
Okay.
I'm doing that.
I will stop sharing this, so now we can see you.
Lots of stuff, Dave. Very interesting. So we have a few minutes for questions. I did want to ask you, you teased us in the beginning. You said it's almost working and you hope to hear in a few weeks. So can you explain what it means by almost working?
Well, the experiments we've done so far tell us that the electrons are in fact getting into the satellite valleys. Okay, but we can't get them out. And this is because we have a heterostructure at the edge where we're trying to get them out. And so we have not managed to balance momentum and energy there so the electrons can get out of that satellite valley into a collector. But we see they're there.
So this is a heterojunction, PN heterojunction solar cell, you're shining light.
Right.
You get them into the valley, but they don't.
Multiple junctions in it. The basic absorber layer is indium gallium arsenide on indium aluminum arsenide, grown on indium phosphide. So that whole structure is lattice matched. Now we were using indium aluminum arsenide N type to try to get them out, but that doesn't match to get the carriers out. There was a barrier there. And what happens is all of that wonderful area out where you have a fill factor all collapsed down to almost nothing. So we just couldn't get the IV of the curve. We had a lot of photocurrent as long as we didn't have forward bias on it. So we've got them in the satellite valleys, but we can't get them out. So the next stage is to go to a material which should match better. And this is gallium arsenide and timonide, roughly 49-51 composition, which is lattice matched indium phosphide and should be a good match to get the electrons out of those L valleys. Cross our fingers.
And they're not coming out, what? Because there's a barrier to.
Barrier.
Yeah, okay.
You see that there's at least one, perhaps two barriers. Okay.
Dave, I have a question.
Sure, Marco.
Can you expand a little bit on what do you think is the effect of the density of states in the different valleys and its effect on the trapping of your phonons, of your electrons?
The scattering rate from, say, gamma to L depends upon the density of final states. And the final states are the L density states where there's one gamma valley, but there are 4 L valleys, and they have a big mass. And so the density of states is maybe 20 times bigger than it is in gamma. And so they stay over there for a long while as well, because the density of states to come back is low.
Yeah, isn't this the reason why they're trapped there and you have a problem in extracting them?
Right. Well, they're trapped over there and they're not coming back to gamma, we're pretty sure. But we don't want it. We don't want them to come back. We want them to get out into a collector material and get them into the contact.
Huh. Got it. You answered the question. Thanks.
Yeah. Okay.
Another question. Thank you so much for the talk, David. It was great
Good to see you again.
Good to see you too. The question I have would be, I was just curious if you had any thoughts about whether or not you could possibly manipulate the populations of the phonons that participate in your 3-phonon scattering in order to cut those decay channels off. Just curious if you had any thoughts about that.
I've not thought about that, but you know, that's certainly a possibility if you could work on those. Maybe by creating them by another process, or for example, put an ultrasound through the thing to shift them away from their resonances and things. There are a lot. I mean, there could well be done by some creative processing, but I've not thought about exactly how to do it. Now you're going to keep me up all night.
We should chat. In my lab, we're using Brillouin scattering to laser
Sure.
cool
So you're looking at
traveling
acoustic.
phonons and to synthesize phonons. So I'll send you an email if you're interested.
Sure, sure, sure.
So, Dave, so do you see this? Is this mainly materials problem? Is it do we understand the physics enough to be able to design these things? Where are the breakthroughs going to come? Materials.
Well, I think it's a materials problem. And it's a double problem. First is finding the material, and then finding out if you can grow the material. Right. And so when I said gallium arsenide and timonide, there's not a hell of a lot known about that material. So I set out to calculate the high field properties of it, and I have a nice long paper coming out in Semiconductor Science and Technology, just on the electrical property, the high field electrical properties of gallium arsenide and timonide.
Okay, so lots of opportunities there.
Absolutely, absolutely.
So there's nothing in your equations that says it can't be done.
No, nothing in the equations. That's true of Ross and Nozick as well. If you could meet their conditions, it would work too. But we've only been at this for 1 year, so we've got 39 more years to get where they are.
Plenty of time.
Sure, but the byproducts is, for example, is once we started growing gallium aluminum arsenide at Oklahoma, that material went to John Bird in Buffalo, and he's been doing low temperature measurements of the transport properties of the quantum wells on indium aluminum arsenide. So the material is going around to various places, and we're learning a lot about the materials at the same time, because indium aluminum arsenide is another material which very little is known about.
Well, look, very good. Any more questions before we wrap this up and let all the graduate students head off to the bars? Oh no, that happens on Friday nights, according to Dr. Ferry.
Yes. However, it depends on whether the bars are open where you're at.
Yeah, that's true.
Now, if I were to go to Texas, the bars are now open.
Very true.
There's no more mask requirement and no more closed down bars. Last time Scottsdale tried that, we gave us a big second bump in the COVID.
Very good, David. Thank you all for turning up. I think that was, I counted 45 or 46 people on the Zoom call, so that's very nice. When we do workshops, conferences, not conferences, when we do talks at ASU, it's hard to get 20, 30 people in a room. So to have 40 of us on Zoom like this is wonderful.
Wonderful, yes.
So Jen, I think I'll hand over now. Maybe we can stop recording in a few minutes, and we make these recordings available after the fact, I believe.
Well, if anybody thinks of something after the thing,